Hi everybody, my name is Alessio Trevisan and I am the Endurica product manager here at Enginesoft. I work on the offshore and construction department and I usually calculate special structures for that field of activity. Um, I'm very happy to introduce Dr. Will Mars, that is a true expert of elastomers, and Dr. Mars founded Endurica LLC in 28 to give product developers a simple and accurate workflow for analyzing the durability of elastomer products. The firm's products and services are used by leading firms around the world to manage durability. By the way, Dr. Mars has received several awards for his scientific contributions and innovations. He has more than 60 peer-reviewed publications, holds 4 patents in the area of elastomer durability, and is the past editor of 2 scientific journals. Today, he will explain us how to align your engineering budget with your durability goals, which is also the title of this webinar. After his speech, there will be the possibility to make some questions. So I give the floor to Dr. Mars without further hesitation. I will.
Hi, Alessio. Thanks for letting me join you on this webinar. It's really good to be here. Yeah, today's topic is one that I'm really passionate about. Uh, when we go to do analysis, one of the most important things to get right up front is your choice of what testing, what analysis workflows you're going to use, and that's going to obviously depend on the requirements of your customer or your regulatory environment, and it's also going to depend on the budget that you've got available. Sometimes there's some rubber parts that are let's say very low margin, cheap parts, and it's not economically justified to go very deep. And then other times you have a very safety critical part that you want to go all out for. And so this webinar is going to give you the hopefully give you some things to think about so that you can exercise the right judgment about which tools you can use. Um, and Yeah, so welcome, and let's dive into it. First of all, just say a few words of introduction about Endurica. This is year number 16 for us. We are 100% focused on durability solutions for the rubber industry. Um, and we provide both testing and simulation software for the analysis of elastomers. Um, and we're this is our team at the moment. We're about 10 people, and 3 of us are PhDs, and we've got a bunch of engineers, and we just recently opened an office in Europe, and so that's kind of our footprint. As far as who's using our tools, every year Rubber News puts out a list of the top 50 rubber companies, and we're in use on 6 of the top 13. So, and then a number of others as well, and a number of OEMs and raw material suppliers. People all across the supply chain are using our tools to get durability right, and we're in a lot of places around the world. I'll just mention our latest, let's say, user case. If you're interested, you can follow the QR code. And there's a video at the end of that you can watch. But this is one of our users at Trelleborg, who's talking about our applications in the rail sector. So very interesting application there. All right, so enough on introduction. Let's talk, I guess, about um, uh, the how to align the budget and the analysis. And if you look at, this is kind of an outline here of the typical uh, content of a fatigue analysis project. Um, and you're going to have, first of all, you're going to have a design, you've got some sort of design goal or requirements or specification that's come from your customer. It's come from government regulations that you have to pass. Maybe it's come from, um, internal requirements, but there's some targets that you have to hit in terms of durability. And those requirements are going to drive your choice of analysis approach. The Endurica tool set really is you should think of it more as a toolbox than a single tool, because we offer a series of different approaches, and you're going to see that they're scalable, meaning that there's some very simple approaches that are very quick and easy to apply, and then there's some very uh, complete and approaches that take more effort but also have more benefit. And so we'll talk about how to align these, but you'll want to choose your approach, and the approach that you choose is going to determine what tests you need to make on the material. Right? We need to characterize material behavior. Um, we need to somehow describe the duty cycle of our part. That could be very simple, like a worst case load, or it could be as complicated as just a raw recording of all the loads going into your part from a track test, data acquisition, and so on. But we'll need that description. Obviously, if you're doing finite element modeling, you're going to need some geometry and some kinematics to describe how the part is situated spatially and how it works. Uh, Whenever we're doing fatigue work, we need to be mindful of how we're going to define failure. Is it the growth of a crack? Is it the loss of stiffness? Is it a change in properties due to aging? And those are all criteria that we can monitor using the Endurica tool set, but we need to be mindful of how failure is defined both in the test and in the simulation. And then finally, the final piece in any analysis project is the validation piece. Um, you need to bring validation, obviously, to uh, justify your confidence in your results. And as you use analysis tools, you always want to have I call it a closed loop, such that when you make predictions, you validate those predictions, and you learn a lot about maybe ways to improve your assumptions about the situation. It's pretty rare that we get everything right on the first try, and so you always want to have test results that you can validate against, depending again on the scope of that you have to work within. All right, so let's talk about some broad categories of fatigue analysis, and the Endurica toolset supports all of these. These are ordered in order from, let's say, the easiest and least uh, expensive, least time consuming to the more sophisticated analysis. So the easiest thing we can do, well, so the three categories are infinite life, safe life, and damage tolerant analysis. And now in the infinite life approach, what we do is we say, when I design this part, we're going to design it such that we're going to select our loads or our uh, properties or our part dimensions such that damage will not be allowed to occur. Just like metals, rubber does have a fatigue limit, and if you stay below that limit, then in a limited sense you can predict indefinite life, right? So the idea in infinite life analysis is you're just checking uh, for your, let's say for your worst load case, are you above or below the fatigue limit? Um, and when you use the infinite life approach, you can calculate I've called it S here, the safety factor, and that just represents the margin by which you are, you know, uh, clear of the fatigue limit, right? So if you're below the fatigue limit, well, if you're right on the fatigue limit, then the safety factor is 1. Um, but if you're below the fatigue limit by 2, then your safety factor is 2. Okay, so that's the infinite life approach. Uh, the next category is safe life, and in the safe life approach, your customer gives you uh, a target life, right? An automaker might say, well, you have to have a 100,000 kilometer warranty for the car or something like that, and so you're given a life target. Now this requires a bit more testing because you have to characterize the rate at which damage develops as a function of your input loads. But once we make that characterization, then we can calculate life and we can check whether we're above or below the limit. That's the safe life approach. The final approach is the damage tolerant. And the damage, in the safe life approach, we're sort of assuming that there's a known load case and that we just repeat it some number of times. And the interest is how many times can you repeat the load case? But if you go out to real life, the loads that you have on day 1, they're never the same as day 2 and day 3. And so you need a much more incremental approach. And in the damage tolerant approach, we track the development of damage in the part transiently as we apply more and more load. We're looking at things like remaining life, and so that's an example of the damage tolerant approach. So Endurica has tools for all these, and we're going to talk through those today. Um, Now, I mentioned that when you do fatigue analysis, one of the very first things you need to think about is materials testing. And so you need to, of course, Endurica does have a materials database, but in general, to get the best results, you're probably going to want to test your rubber material. At least, well, like I say, again, it's a question of scope. So, if this is a context where you don't have the luxury of testing, you can use the Endurica materials database that's included with the software, and that's maybe the cheapest option. Um, the uh, but our materials testing framework is scalable, and you can bring in as many of these various effects as you need to do to sort of capture as much accuracy as you can within your time and engineering budget. So I've colored the first 2 tests yellow because typically for any fatigue analysis that you're going to do, you're going to need to measure the hyperelastic module and the core module. The hyperelastic module is the stress strain curve for rubber in simple planar biaxial tension. It also characterizes the Mullins effect, which is a transient cyclic softening that rubber will exhibit, and so we'll characterize that. And that's just required just to set up your finite element model in the first place. The core fatigue module is where we measure the fatigue crack growth rate curve under fully relaxing conditions. And we also measure a few points on the strain life curve. And from those 2 experiments, we can determine the initial crack precursor size of the rubber. So those are the 2 required experiments. Um, and then depending on your application, there's all sorts of other things that we can think about. Um, we can measure the fatigue limit. We can measure the strain crystallization, which has an effect on mean strain effects. We can look at aging of the rubber. We can look at time-dependent behavior, like creep. We can look at the dependence of rubber fatigue on temperature, self-heating and temperature gradients. We can look at cyclic softening. We can look at ozone attack. These are all options that we can add to these. And so it's a very modular framework, and you just do what you need, but very scalable. So now, if we take these testing modules and kind of map them onto this framework of infinite life versus safe life, you can kind of see uh, uh, this is just a mapping of where you might use any of these modules. So if you're using the infinite life approach, you're definitely going to run the hyperelastic. You're going to run the you're definitely going to run the intrinsic strength, which is the fatigue limit. And then you might also run the reliability module, which is where we measure the distribution of crack precursor sizes in the rubber. That's optional, but you might be interested in the statistical character of that. If you're running the safe life approach, then all of these modules are possible, with the exception of the cyclic softening module. And of course, if you're doing damage tolerant, then you may be potentially using any of these. Now, that's not to say this is a map of what you have the possibility to use. That's not saying that you necessarily are required to use all of these. Yeah, I've kind of labeled here what's required and what's let's say optional, depending on your application. Now, when you use Endurica, there are three tools that we talk about. One is the Endurica CL, and we have Endurica DT, and we have Endurica EIE. The CL, and they're really divided by the kind of workflow that they support. So with Endurica CL, it's a post-process only workflow where you run your finite element model, you run Endurica CL as a post-process on the stress strain results from the finite element model, and then it outputs either safety factor or fatigue life. That's Endurica CL. So the key thing there is it's a single duty cycle, and you're talking about, repeats or safety factor. DT, and so you can see this kind of maps onto the first two categories, right? This maps onto infinite life or safe life analysis. Endurica DT is our incremental solver. And with Endurica DT, you can specify block cycle schedules. You can do co-simulation. It's not with DT, it's not purely necessarily a post-process only. With Endurica DT, you can couple the Endurica solver with your finite element solver. And for example, if you have cyclic softening, you can update the stiffness with cycles to, like, if you have a stiffness loss type of failure mode. So that's the DT tool. And then finally, the last tool is what we call EIE. Now, that's an acronym that stands for Efficient Interpolation Engine. And this is a tool that we use when we're working with road loads that we've recorded from the track, or maybe that have come from a vehicle dynamics simulation. In many cases, the histories that you want to analyze, they're lengthier than you can really analyze directly with a finite element simulation. And so Endurica EIE provides a method whereby you can rapidly convert, XYZ global force or low displacement inputs and convert those into stress strain history on each element in a model without having to do the full blown FEA. It's very fast. It's like 10,000 times faster than trying to directly do it. So it opens up a lot of analysis possibilities that are important. All right. So now what I want to do is just go through some examples to kind of make all these ideas concrete. And you can kind of see that as we're going through these examples, we're scaling up the both the materials testing and the analysis requirements. So the first example that we're going to do is just an infinite life analysis. Again, the right context for this is when you have maybe a very tight deadline or a very small budget to work with. This is just a way of checking, is it above or below the fatigue limit? If it's below the fatigue limit, then you've got, a reason to say that you've satisfied the design requirement. If you've now, yeah, so microjack is one example. We'll also do the example from an automotive suspension, a sway bar link. And then we'll also do a tire example. You can see here that as we go in, the materials characterization gets more and more sophisticated. And you can also see the tools that we're applying in each of these particular examples. So, all right, so let's talk about the first example. So, like I say, rubber has a fatigue limit, and what you're looking at in this plot is the crack growth rate curve for rubber. You can see that on the x-axis, we're plotting the energy release rate, or some people call it the tearing energy of rubber. Right, this is the, let's say, the intensity of the load, the stress or the strain is related to this, and you can see that well, there's a critical value of TC, and if you exceed that, the part ruptures. It's a strength problem. If you decrease the tearing energy input, um, the rate of crack growth gets slower and slower and slower. Eventually, as you reach this limit T naught, the crack growth rate will actually drop to zero. For a natural rubber, for example, T naught has a value of something like maybe 50 joule per meter squared. And if you're below that, then the crack does not have enough energy to break any polymer chains, and so it doesn't grow no matter how many cycles you give it. And so the whole idea in infinite life analysis is, first we measure T naught, and then we calculate what is the margin between my worst case load, which is hopefully below T naught. What's the margin between that worst case load and T naught? So here's an example of the materials characterization. Um, this is just showing the input fields in ANSYS. So obviously we need to know the stress strain behavior. Um, and this is an Ogden model that we've happened to fit for this example. We've also measured, this is for an EPDM compound, and we've measured the fatigue threshold at 60 joule per meter squared. We've measured the mm, initial crack size at a tenth of a millimeter. And I should mention, Endurica, when you're using Endurica, it always assumes that your material contains microscopic cracks. And one of the important inputs for the material characterization is, what is the initial size of those cracks? We can measure that experimentally, or you can make an assumption about that. Typically, they're in the range from 20 to 100 microns. So you can see in this case, we've used a sort of a conservative assumption of a tenth of a millimeter. But again, very simple characterization, and that's an advantage, because if I just specify my hyperelastic and my intrinsic strength properties, I don't really need to worry about a lot of the other special effects that rubber might exhibit. Temperature and rate dependency, I don't have to think too much about that. Um, Crack growth rate curves, strain crystallization, all of that I can just kind of ignore, because that's not going to come into play in this analysis. So here's an example for this micro jack. We just want to apply this displacement where we're sort of flexing the connector here to, and hopefully we want to show that the design is going to have an infinite life capacity. So first you run the simulation in ANSYS, and and then after you've run and you have the stress strain results for the simulation, when you fire up ANSYS Mechanical, Endurica has a plugin that will give you a couple of new buttons. There's an export button, a button to run the job, and an import life button. Um, so you can just export the strain history results, um, and then you'll run the job, and then you'll import the results back to ANSYS. So you'll do the visualization inside the ANSYS environment. When you do the export, you're going to see some forms that look like this. You're going to select the particular elements that you want to analyze. Here we've got some metal elements that we're not going to analyze. We're really interested in the insulating rubber in this analysis. So we just select the rubber. We select all the time steps that we want to include as part of the analysis. We tell Endurica what type of results we're sending it. In this case, we're using bulk 3D with hydrostatic pressure. And then you hit the export button, and you'll be able to send those results out. And then Endurica will, and then you go ahead and submit the job. Endurica uses a procedure called critical plane analysis, And critical plane analysis is the idea that your part contains cracks in random orientations, but the orientations that actually develop in service are the ones that that minimize the life or minimize the safety factor in this case. So what we do is we calculate this for each point or for each element centroid in your model. We're going to basically scan through all of the possible orientations that a crack might take, and for each of those orientations, we'll calculate a tearing energy, and then for each of those tearing energies, we'll calculate the safety factor, right? We'll just check, is it bigger or smaller than T naught? And of course, the safety factor then that we report back to you is the safety factor that is the smallest value across all possible orientations. Um, and now this sphere is what we call the safety factor sphere. It just, here what we've done is we've colored the surface of the sphere according to the safety factor, where each point on the sphere is the normal of some plane. All right, and so in this case, I've plotted the safety factor as a contour, color contour on the model. I've zoomed in so you can see the element with the shortest safety factor. In this case, we might see a safety factor of like 2.3, which tells us that that this design is okay, right? We can expect indefinite life, and now if the safety factor had come back as 1 or less than 1, that would tell us that we don't have infinite life. Now, a limitation of this analysis is that it will not tell you if your safety factor is less than 1. This analysis obviously does not tell you how long the part might last, and so that's a limitation of the infinite life approach. But when you're looking for quick and easy, this is a great approach for doing quick work. So here's kind of a summary. You can use infinite life design to screen materials and concepts. It's very fast. It'll give you some insight into the basic failure mechanics, right? It'll show you where it'll fail. It'll show you the orientation of the critical plane. Um, it sort of airbrushes away all of the special effects, so you don't have to worry about getting lost in a lot of complexity. Um, and yeah, so simple and fast. Obviously does not consider aging, does not consider other special effects, does not give you any life if your safety factor is less than 1. So if your safety factor is less than 1, then you need to move on to the next category. Well, you either need to redesign your part or move on to the next category of analysis, which is safe life. So for the safe life, I'm going to illustrate this analysis with a sway bar link. This is part of an automotive suspension. It's loaded axially in the X direction. And now here the materials characterization gets a little bit more sophisticated. So we're going to do the hyperelastic, the core, and now we need to characterize the mean strain effects, right? With the non-relaxing module. Um, so the materials characterization is going to look something like this. We're going to have stress strain curves just like we had before. We're going to have a crack growth rate curve, which we did not, before all we needed was the fatigue limit. Now we need the full crack growth rate curve. And we also need the strain life curve so that we can use these two results to calibrate the crack precursor size, which for this example turns out to be 12 microns. Once we've defined all these, we can also run the non-relaxing experiments. That allows us to define mean strain effects, and we can plot out, for example, a Hay diagram for the rubber. You can see here's the Hay diagram. It's quite a bit different than what you might see for metallics. Metals look like a straight up triangle. With crystallizing rubbers, you get this interesting hump. We recently did an article on this in the Futurities magazine, so check that out, and you can learn more about strain crystallization effects. So once we have the materials characterization for the safe life approach, then we're going to want to do the fatigue analysis, and we're going to want to use now that the history for safe life can be as simple. It could be as simple as just a sine wave. It could be as complex as you want. You could have very you could have a road load recording, which in this example, that's what we're going to do, mostly so I can show you what EIE does. But so in this example, we're going to have the displacement varying from 0 to 4 millimeters over 1,000 seconds. And now, of course, it would be very expensive to run a finite element job through this 1,000 seconds of history. But if you look at this, now this is just in a displacement in a single direction. But if you look at this, you might say, well, why don't we just model the displacement of the part from 0 to 4 millimeters? And since this is nonlinear, maybe we take 8 steps to do that. And then when I want to know what's the strain at any of these times, I can take these results from the 8 steps that I computed, and I can just interpolate between the steps, right? So it's kind of treated as piecewise linear and just interpolate. So that's what Endurica EIE does. So this pre-computed finite element solution, we call this the map. So with EIE, you compute a map, and then you can use that to interpolate whatever strain history you've got based on your input displacement history. Now, this example is just one channel of load. EIE can accept maps that have as many as 6 independent input channels. But to keep things simple, we'll just do it on one channel here. And then what EIE does is once it interpolates, then for each element, we will get the full time history of the strain, so that we can pass that to the fatigue calculation and get fatigue results. So here's kind of an example of the EIE workflow. First of all, we need to define the map. In this case, it's very simple. It's just running from 0 to 4 millimeters displacement. Once you set up the map, you run your finite element job. And then you need to also give your history, which is the history of the displacement. And then you're ready to go ahead and do the interpolation by running the job. So again, these are the steps for building the map. First of all, you specify how many channels and what each channel means. The channels could be force, they could be displacement. Any variable that you can use as a boundary condition can be an input channel. Then you define the particular path that your map solution is going to follow in the finite element job. In this case, again, it's trivial. We're just going from 0 to 4 millimeters, but you can imagine if I've got multiple channels, I have to trace out what path my finite element solution is going to follow to build the map. That can be done in one job or a series of jobs, up to you how you want to structure it. But once you've got that defined, then you can run your finite element job by applying those boundary conditions. And then you basically associate the map with the finite element results databases, and then you're ready to go ahead and run EIE. So in this case, we're going to go ahead and run EIE, and this is what the map job looks like. And then once you've run EIE, then you can pass that into Endurica CL. Endurica CL will compute the repeats of that 1,000 second history, and it'll report. So here, when it says the red here corresponds to 30,000 repeats of that 1,000 second snippet of history, and so here's your prediction of the life and the failure mode. And that's an example of safe life analysis. Sometimes I get the question of the validation case for these, and I just wanted to throw up one example. This is one that one of our users published not too long ago, 2022, I guess, just showing that they're they made in the CAE simulation, they predicted a life of 520 repeats. This was using road loads, and in the physical test, they actually found on average about 523. So it was a very, very good correlation, both for the life and for the prediction of the location of the crack. You can see the crack right there, and you can see that's exactly where we're predicting life. All right. So again, you could use safe life to justify, if you've got a spec on what the load case is and a spec on how much life you need to get, this procedure allows you to do that. The materials characterization is a little bit more involved than the infinite life. right? You have to get the crack growth rate curve. Maybe you have to start thinking about some of the special effects in rubber. But it does allow you to compare A to B on, lives longer, lives less long. Gives you very detailed knowledge of damage mechanisms. Um, and, flexible, scalable, accurate, and so on. Now, the only trouble with this is that, again, you've assumed that you've got one load case that just repeats on and on and on until end of life. And real life is, not really that simple. Um, another limitation of the safe life analysis is, since it's post-process only, it means that if the material properties of the rubber evolve with cycles or with time, the safe life approach can't do anything with that. So if you want to take that kind of stuff into account, then you're going to have to go a step deeper to the damage tolerant approach, and you're going to have to use some of the co-simulation capabilities. So to illustrate the damage tolerant approach, I'm going to use the example of a tire. And in the tire industry, there's a government test where they assign a speed rating to the tire. And the way that works is there's a test that has 13 steps in it. So you can see each row in this table is one of the steps in the test. They start off in the first 4 steps, they run at 85% of the rated load of the tire, and they start at 80 kilometers an hour. They do that for 2 hours. Then they bump up the speed to 140 kilometers an hour for half an hour. And you can see basically in each step, they're increasing the speed on the tire. At the end of step 4, you've accumulated, what is that, 3.5 hours of tire operation at various speeds. And now if the test passes this, it's legal to sell the tire. But this does not get you a speed rating. To get a speed rating, you've got to now put the load at 100% of rated load and then keep ramping up the speed. They run these in steps of 10 minutes. So they'll run the speed for 10 minutes. If the tire hasn't failed, they bump it up to this one. If the tire hasn't failed, they bump it up to this one. And they just keep going. The test spec goes all the way up to 300 kilometers an hour, which is kind of crazy. But if you're racing, you probably want to make sure your tires will do that. So anyhow, so this is the test spec, and basically the speed rating that your tire earns is the last step that you pass in the test. So to use the damage, in this example of the damage tolerant procedure, what we do is we model each of the test steps individually, right? So this is 13 different load cases, basically the tire running at speeds ranging from 80 kilometers an hour to 300 kilometers an hour. There's the different loads are applied here, right? The first 4 steps are 85% load, and the rest are at 100% load. And here I'm just showing the out of plane displacement of the tire so that you can see up until about 200 kilometers an hour, the solution is pretty, let's say, tame. If you look in the colors in the sidewall, you can see a little bit, as we increase the speed, you're starting to get a little bit more displacement, right, because of the growth of the tire with the centrifugal force. However, there's a speed where once you hit a critical speed, the tire starts to develop a standing wave. And this is very damaging to the tire because, but below this speed, you have 1 fatigue cycle per rev of the tire. But as soon as you hit this speed, now you have, 10 cycles per rev of the tire. And so again, that becomes very damaging. So in these types of problems, it's often very important to look at the thermal effects, right? If we're thinking how temperature influences things, then we need to calculate self-heating, which we can do. This is just showing temperatures in the simulation as a function of the test step. You can see that in the first 9 steps, increasing the speed does increase the temperature, but once you hit the standing wave, the temperature just shoots way up. Now, of course, when you're just running the structural and the thermal finite element models, we haven't calculated damage yet, so we can sort of calculate a notional a notional stress strain field, a notional temperature field, a tire is never going to reach 200 degrees Celsius because the rubber is going to, catch on fire and burn before it hits 200. But if you ignore the fact that material can fail, then the stress strain, the temperature fields will give you this information. And now we need to use the damage tolerant approach to accumulate the damage and find out in which of these steps are the conditions so severe that the tire is done. Um, so now, of course, when you're doing this type of simulation, not only do you need the hyperelastic, the crack growth curve, the crystallization behavior, but now we also need to think about, well, how does the crack growth rate curve depend on temperature? How does the tire age? How does the tire respond with aging of the material? And we have tests for characterizing all of those things. This is just a plot that shows the dependence of the tear strength of the rubber on temperature up to 200 C for the belt, the sidewall, and the tread of the tire. And you can see that there's some rankings. Some of the rubbers are more sensitive to temperature, some of them are less sensitive. And so that's an important part of this calculation that involves very high operating temperatures. Um, and then in the damage tolerant approach, we're computing residual life as a function of time through the 13 steps of the test. And what residual life means is we've got kind of a load case that we can use to measure the life of the tire. So in this case, we've just taken the very first step of the test and we've said, if I took that first step of the test and ran it out till end of life, that's my measure of residual life. So at time zero, before there's any history accumulated, there's a residual life on the tire. Let's say 2.5 times 10 to the 7 revolutions of the tire. Now, after the first load step of the test, if I accumulate those cycles and temperature field, you can see that the residual life does not change very much in the first 2 hours of the test. Um, and then as I keep accumulating, you can see I get to the Q step, the R, the S, the T. You start to see a little bit of just a slight decrement of the residual life until we get to we pass step H, and then we go into step V, and you can see that at step V, then the tire loses integrity, and we've got failure. This is actually a case where we looked at 3 different analysis cases, and you can see we had different speed ratings on these tires. If you want to read more, there's a QR code you can scan, and that goes to an open access paper that gives all sorts of details about this analysis. But obviously a more sophisticated analysis, we have to measure more things about the material. Also, we have to take a lot of care around setting up the co-simulation. That involves a Python script that ties together the finite element simulation and the Endurica calculation, and there's the iteration loop. So it's, like I say, it's a little bit more sophisticated, but absolutely very doable. And so that's an example of what we can do with residual life. And just as a further example on this, this is the same type of analysis looking at residual life, but this was a residual life analysis we did for a tire following a tire impact. So in the animations, you can see the obstacle, 150 millimeters tall, hitting the tire, setting up some waves around the tire. So in this simulation, we did a half an hour break-in, then we did the impact, and then we did a run out. And what you're looking at in these contour plots is the percentage change in the residual life relative to the case where you don't have the impact. And you can see that when you do the impact, it produces a bruise on the tire. And you can see where most of the damage in the tire is happening. If you peel this away, you find out that this does some damage to the belt structure of the tire. So yeah. All right. So those are some examples of damage tolerant analysis. If you've got multiple load cases like block cycles or multi-step tests, if you've got aging or cyclic softening, right, that causes material evolution. And anything that is an incremental type of workflow or a co-simulation, that's when you would use damage tolerant. We recently published a paper on modeling the effects of oxidation on fatigue, and that's another example where we would use this incremental workflow because the material properties are changing with time. Um, so obviously you can be very highly realistic in terms of material properties and in terms of your duty cycle. And the only limitation really is just that you've got to specify things more completely, and uh, and there's some more work for the analyst to do around, tying everything together to build the workflow. So I'm going to stop there. I think there's time for questions. Yeah, I sometimes when I talk to people and we show them our tool sets, they not all the time, but sometimes people will say, "Oh, that sounds really expensive," or "Oh, there's no way you can possibly be accurate not enough to predict rubber fatigue," or "That's too hard." And hopefully you come away from today and say, "No, there's tools for that, right?" And part of the trick is choosing the right tool for the job. You don't want to use a screwdriver where a hammer is needed, or vice versa. But if you're mindful about what your time limits and your budget limits are, and you can choose an appropriate analysis. And the Endurica tool set is very scalable that way. It'll give you what you can do to get durability right. One of our mottos is accurate, complete, and scalable. So we give you the material models you need to be accurate. We give you all the workflows you need to have a complete tool set. We're scalable so that you can go from small problems to big problems, and just get the job done that needs doing. So, um, all right. So I think if there's any questions, you could enter those in the Q&A, um, and I'm happy to stay around for a little bit and uh, answer any questions on here.